Hey guys, let's get started. All right, so week 15, last lecture. Now that's today. No neural networks today. It's a totally different idea. It's more similar to KNN from the beginning, but we'll cover a lot of interesting ideas in this one. I usually like to finish with this topic. Um, because it covers a lot. It's pretty interesting. So I'll do two examples actually of it. One is just with language and text, just to understand. And then we're going to do one where we apply it to cybersecurity, and you'll see how you could use it for so for something called an intrusion, no, sorry, an anomaly detection system. All right. Yeah, so let's go ahead and get started. So I'm going to click on this one. So this is unsupervised learning and K-means, not to be confused with KNN. Similar idea, a vector space model problem, but no labels, right? So everything you've done, you've had an image and you knew it was a cat. You had another image, you knew it was a dog, right? So you've done that a lot in everything. But in this example, or this problem, we will have no label. So instead, we just have the features. So it's like having the images and we don't know what the labels are, or having the iris data, the feature vectors of 4 features, but we don't know if it's setosa, virginica, or versicolor. So what do we do? But the model gives us classes. What the classes are, that's not clear, but it's what the model looks for patterns essentially in the data and creates semantic classes of similarities between groups, right? And so that's kind of what we're going to do. So if you want to read some of the slides, here they are. I'll just jump into the code. So I provided the link here, right? And it's these two scripts that I have here. We're going to start with this one, which uses text. So it should be pretty intuitive and clear to understand. And then the other one, it'll be the same, pretty much the same code, but the data is different. It's going to be more similar to network data. It could be malware data, hexadecimal data, whatever it is. All right, so we're going to go ahead and start with this one, unsupervised k-means. And that's, we'll wrap up the semester with this topic. So I'm going to try Colab, I guess, to keep things simple. We don't need a GPU or anything. This does not require anything like that. But, keep it simple. The data is provided, so we don't have to read the data. I actually just create the data on there. All right, so let's start. So latent. So this is sometimes is an old-timey term called latent semantic discovery. Latent just means something that's kind of hidden, not clear. Semantic just means that there's meaning in there, which is really incredible, right? Really powerful because you'll see that this tells you something very interesting about the human brain, right? So we're going to look at that. So the libraries that I'll be using are basically sklearn, NumPy, so we're, the basic ones. Let's go ahead and run this. Okay, perfect. We are also going to look at a topic called truncated singular value decomposition. This is also called PCA. And we're going to see it from the applied side, how that is actually really helpful. Okay, so that will be very helpful, and I'll give you the reasons why. So I have some data. In this case, is actually text data. I have 7 sentences. You guys see that? I have the sentences are machine learning and Python are super fun. That's one. Python is super, super cool. Statistics and data science are cool too. Data science and Python are fun. Python is great for machine learning. You guys see that? So that's 5. Then I like football and it is great. Football is great to watch and I like it. Okay. So I just give you these 7 sentences and I ask you to create 2 clusters. What would these clusters be? Like, how would you group these sentences if you can group them into just 2 clusters? Separate out the sentences into just 2 clusters by similarity. How would you do it? Sports and coding language. Where'd you get those terms, first of all? Coding, right? So think about what you did. You did like 2 things. First of all, you took some sentences and you said these are similar. And then you have to do 2 groups. So then you group them into these 2 categories. And then you actually created these categories, right? You said sports and coding. Think about that. So what we're going to do is I'm going to discuss a technique and an algorithm that can actually do the exact thing that you just did. Think about that, right? So that thing that seems, if you ask a person, they would say, oh, that's only humans can do that. But actually a machine can come very close, right? And so the question is, are machines super sophisticated like the human brain, or is the human brain super simple that a machine can imitate it? Do you see what I'm saying? So is that process complex or simple, right? And what is the brain doing? Is the brain doing this? That's one question we don't quite know, right? We have this of the grouping, but we don't know if your brain actually solves it the same way or if you just have a totally special way of solving it. But yeah, so these are the examples. I have my 7 sentences. So the first thing we need to do is obviously we have learned all semester that when we give information to our models, we have to give it numeric data, right? We can't just give it text data. It's not going to understand that. So we're going to have to convert this data into something called one-hot encoding. Okay, we're going to have to do something called one-hot encoding. All right, so we're going to do that. And the way to do that is to use something called a count vectorizer. So it's a library that I'm going to use. Count vectorizer. Stop words just means the list of stop words in the English language. So the, of, a. Those are stop words and they're going to be ignored. Okay, so they're not gonna. So for instance, the word is not going to be included. Only critical words are going to be included. Okay. So we instantiate the vectorizer from count vectorizer. Then we are going to fit and transform count vectorizer using the data set that we have. So I'm just going to give it the 7 sentences. Each sentence is a separate sample. Hit run, and then I have my DTM there. Okay. And now I'm going to print a pandas data frame just so it looks better. All right, so I'm going to convert this into an array. The index are the examples, and the columns are the words. So I go ahead and run it, and you can see this is called one-hot code. Okay, so it's called an embedding of a type, but more correctly, it's called one-hot encoding. So what did I do? I decided that vectors are going to be, say, of size 11. So I picked 11 words. I have to go into all 7 sentences and find 11 unique words that I think are important, maybe by frequency, etc. And that's them: cool, data, football, fun, great, learning, machine, Python, statistics, super, and watch. Then for each sentence, I count the number of times that I see that word, right? And I mark it here. So for instance, fun appears, so that's a 1. learning appears, so that's a 1. Machine appears, so that's a 1, and so on. Notice that here in the second sentence, Python is super, super cool. Super, super appears twice. You guys see that? So I'm essentially counting this. Okay? That's called one-hot encoding. So this is really interesting because up until like 2012, from since the 1940s, etc., this was the methodology to represent sentences. Do you see that? This is how we would represent sentences. And this is here it looks kind of nice, but this is actually very problematic because in anything related to natural language, you're not just going to have 11 words, right? A vocabulary can be how many words? A vocabulary can be what, 50,000 words? So what does that mean? If you're using this approach, that means that your vectors need to be of what size? 50,000. So that you have a vector for all the words. Do you see that? So that's pretty big already. Imagine now we have 50,000, we have vectors of 50,000 that we're using to represent sentences. It's going to become a very sparse matrix also. Why? Because most of the 50,000 for a vector are going to be what? 0, correct? Very few will be 1. Even here, in some cases, most of these are zeros, and some of them are 1s. But I'm only using 11 words. If I was using 50,000 words, that's even, that's worse. So that's not, in this example, actually, this is still pretty powerful and it's going to work. But for large language models like ChatGPT, we do not use this approach. Okay? So we don't use this approach. Instead, what we use is the following. It's a, similar approach, but not quite. Here, I'm trying to represent sentences as vectors of 11, right? Let me switch to the whiteboard. So, I'm not going to talk about ChatGPT per se, but I will talk about this. So here we have a sentence, that you guys saw. These are the words. You have to then, obviously you can't give text, so you represent with a vector. You represent with a vector, but a vocabulary for any, let's say that you're analyzing books, you're going to need a vocabulary of 50,000 words minimal. So that means that, each one of these is a word. Cat, box, and so on. So you would literally need to have 50,000 columns. So that's a very large matrix where most of the values would be 0 and only a few of the values would be 1s. Become a very sparse matrix. So that's pretty problematic. So instead, what we want to do actually, the goal is to represent text as vectors that are much shorter and also very dense. So that means no zeros. So if zeros have no meaning, you actually want to have values. Okay, so the trick that is used is actually that you take a word, cat, and you say it's a 7. You give it an integer. And then you have another word, car, and you say that's 512 or something, and so on, right? So you assign these numbers based on frequency. You can also do it something equivalent to syllables called subwords. And then each one of these words is represented as an embedding of the same size. So for instance, now what you still have a vocabulary of 50,000. So now what you do is you train a neural network that is of size 50,000, right? Where you have car. So car at 512, it's a 1. Everything else is a 0. And this is called one-hot encoding. You see that? And now you build a network also to produce over here another set of words, but of the same vocabulary, 50,000. Okay? And you build this through a neural net. So it's almost like a classification problem. You give it this, right? And it's going to predict some other word over here. It could be the same word. So it could be like car, in which case it would be 512. So it needs to predict a one-hot encoded vector, right? Like that. Do you guys understand this? But it could be another word. It could be words that are associated with car. So what's a word that's associated with car? Tire or fuel, right? So that could be, the key is that doesn't matter. What matters is an input vector comes in, output vector comes out, and this is a neural network. But it's a different kind of a neural network. It's what is called an encoder-decoder architecture. So you build layers that are smaller until one central layer, let's call it the latent layer, and then we start decoding. So this, I wanted to make this a little bit bigger. So this one should have been a little bit bigger. Okay, so this one, like a little bit bigger, right? And then this one also much bigger. Do you see that? So it's like a funneling in that direction and then unfunneling. And this is called encoding and decoding. Do you guys see that? The key thing is essentially, and you specify this arbitrarily. So you say, okay, and by the way, I want this to be of size 256, only 256 neurons. So what happens now is you train the model with massive amounts of data for whatever your task is, right? And now that you have whenever you give your model this vector of encoding, it will produce at some point a representation of this that is this small, of size 256. Do you see that? And that's what you want. So you can essentially, instead in your network, instead of using these vectors now, you can just use these vectors. So it's encoding, like almost like a compression, like you have learned about compressing things. Do you guys understand? And it's all done through a neural net. So you're training a neural net essentially just to shrink a vector of 50,000 into a vector of 256. And all your words follow the same architecture. So all the words are a vector of 50,000 initially, and you only use this part of the network, that embedding of size 256, and that's what you use from now on. Got it? Yeah, go ahead.
So is the reason we're doing all of this encoding and decoding in order to kind of shrink the amount of data that we're feeding the neural net, which would decrease how much time we need to spend training the model?
Time, and also it's packing the information in a more efficient way.
Okay, so this is all for efficiency's sake.
For efficiency and for capturing knowledge. So you want to capture information efficiently. Both things.
Okay.
You see that? So the problem with this one, imagine a vector that is 50,000, but it's all zeros and just one for one word. That's very inefficient. It's called a very sparse matrix. Instead, this is going to have 256 neurons, and each one has numbers in it, not zeros, but actual data. So it captures more information depending on the task that you're doing. Like I said, you could be comparing these to the same word, or you could be comparing these to other words, but that are associated with that word. Like if a car, then a tire, fuel, driving, you know what I mean? So what is it capturing? It's capturing that relationship. So for instance, let's say that I do cities and countries, right? So I do Paris, France. So the capturing of the data here captures that relationship, that somehow Paris and France are related. Do you see that? So if I ask questions about what is the capital of Paris, it's got some information in here. Or where's the capital of France? It's got some information there about Paris. It's not written there, but some of it is captured
And is
because of the relationship. Yeah.
this relationship based on how similar the vectors are to each other?
It's based on the fact that you're saying for your problem, I see these words together a lot of the time.
Oh, I see.
You see that? So for instance, I can train this model. I can give it this, and I want to predict 5 words that it sees that you see together all the time. So the weights get adjusted to understand that relationship of the correlation of the word. You see that? So that's, but this is just one example. The transformer doesn't actually do it exactly like this, but it's similar. It's the same framework where you put a one-hot encoded vector, which is an integer, a vocabulary of about 50,000, and then you just have to figure out what you're comparing to. And the beauty of this is the weights of the network get adjusted accordingly. Okay, so this is and so now the embedding is much smaller with meaningful information, whereas before it was a huge and mostly zeros, and one is not exactly very useful, right? And so this is the approach today, okay, that is used, and this is what actually this was the approach in 2014, something called word to vec. Transformers from 2019 are a little bit more advanced than that. Okay, but similar idea. Essentially, words get represented by a, so you would not, so whenever you're using car in a neural net, you would not use this one, but instead you would use this one. You would slice that out, that vector of 256, and that becomes the representation for the word car. And all the other words will have vectors of the same size. Okay? All right, so let's go ahead. This is pretty important. This is actually the key that made language work. Okay, so what I'm showing you today is just bag of words approach, which is what I showed you. It's essentially, as we can go back to the code to share the screen. Okay, so we're going back to this. So as you can see, I have taken all, I created vectors of 11 words for my example, 11 words. And I take a sentence and I just count the number of times that I see each word there, right? So for example, I like football and it's great. Remember, we ignore things like I, because those are stop words, but like should be there, right? So like appears once. Football is there, appears once, and great is there and appears once. So if you look at this vector, it has 3 ones and the rest is all 0. But even this works for this example. It's just not the best representation. Got it, guys? All right, so now let's keep going then. So let's add a few more cells. So I have my vector, one hot encoded vector. So now the vector space model, right? What did we say about the vector space model? If I have, and actually I'm going to go back to this is another topic we covered at the beginning of the semester, but I'm going to cover this now. So we talked about the vector space model, right? So if I have a sample with a vector of size 2, right? I have 2 and 4, 2 values, F1 and F2, right? That can be easily represented graphically, right? So I can plot this easily, right? So that's F1, that's F2. So this is like 2, 4. So that's it. So sample, let's call it sample 1. Do you guys see that? You knew this, right? Now, let's say that I have S2. Okay. But S2 has 3 values. F2 to 4. So that's F1, F2, F3. This is called vector representation in the vector space model. So what does this graph look like? Can this be plotted? Yes, it can. So it's F1, F2, F3. This is R3. This is R2. And we can even visualize it with our own eyes, correct? Nobody disagrees about that. So now let's go to the iris data set, S3. You know, how many columns or features that we have in the iris? Do you guys remember? We had 4, right? Everyone with me? Now, can you plot a vector of size 4? No, you can't, right? Humans can only see in 2D, 3D. We can't have no way of perceiving a fourth dimension. But this is essentially what this is, right? So this is R4. It's the it's a fourth dimension where the axis would be, I don't know, somewhere like there, and that's perpendicular to all the other ones. That's a fourth dimension of F1, F2, F3, F4. Do you guys see that? So we cannot view it, unfortunately. But we can, the math, thankfully, the math holds. Whether this is R4, this could be R11, could be the famous MNIST data set is R784, correct? If we spaghettify the images, 28 by 28. We can view the images. We just can't, in a vector space, plot those images as points. Remember that everything becomes a point in that vector space. Do you guys see that? Does that make sense? So we cannot do that. Now, let's think of our current example. Our current example is text, and we have 11 words, I think it was. Let's say it's 11, right? And it's mostly zeros and ones, right? So this is 11, so this is R11. We cannot plot this. It's not possible. Wouldn't it be nice if we could see one set of sentences plotted and, but we cannot. However, what we can do is we can compress the data. And there's compress the data. And there's several techniques for doing these. Some of these are very statistical, but we can also use neural networks. I literally just showed you how to do that, right? With the embeddings. We talked about that a second ago where I said, I can just create a neural network, right? Create a neural network of size 50,000, and I'm going to use this layer. And I can say that layer is 10, 20, 30. It's essentially a compression of it. Do you guys see that? But there's also these very traditional, historically very powerful and well-known techniques for compression, not using neural networks, using other areas of statistics. And 2 of them are called singular value decomposition, which is a really nice one, SVD, and truncated SVD. It's based on linear algebra. And then there's another one called principal component analysis, PCA. So they're 2 powerful techniques. Essentially, they compressed our data. So in our example, we're going to use sklearn to take our vectors of size 11. We're going to feed them through SVD, and we're going to produce equivalent vectors of size 2. Do you guys see that? So we're going to compress them. Now, when you do this compression, there is some loss of information. But that's the thing that you try to be efficient about, right? So if you're lucky, you can compress the data, but the data is still useful, and you only let's say, for instance, that you can say, I compressed it and I lost 20% of the information. Do you see what I'm saying? So it's like, yeah, you lost some information, but you can still get your model to work, and you can do one thing. what's one thing that you can do with a feature vector of size 2 or even a feature vector of size 3?
Classification.
Classification, but what else? The thing we were talking about before, we can plot it. Do you see that? So you cannot plot a vector of size 11, but you can plot a vector of size 2 because this is just f1, f2, which essentially means, so now the 7 sentences, even though initially the vectors are of size 11, can be plotted by doing this compression through singular value decomposition. Do you guys understand? And we could do this also through a TNS. I think, is the name of the algorithm that does the exact same thing using a neural net. So you can do that. All right. So that's the idea. So now let's go back to the code. And like I said, today we're covering a lot of topics, but it's pretty interesting. So you can see that here. So I have my data, and I'm going to instantiate singular value decomposition, this algorithm. And I'm telling it that I want it to compress things into just 2 features. So it's going to train, and then it's going to take a feature vector of size 11 and produce a feature vector of something like size 2. Okay. So we have that. So I'm going to go ahead now. And I'm going to, this object that I just instantiated called truncated SVD, I'm going to call it LSA. I'm going to fit and transform it using DTM, which is my data here. Okay. So the goal is that it looks at the data, it does the analysis, and it should compress it. There we go. So DTM LSA. So now what I'm going to do is the same thing I did before. So the same data frame that I did before, but with a compressed version, right? So you can see I'm grabbing DTM LSA over here, and I'm naming the columns now. Instead of being 11 words, cool, data, football, fun, great, learning, it's going to create SVD1 and SVD2. Do you guys see that? So I have literally now taken the same 7 sentences, but compressed them into vectors of size 11. Does that make sense? If you notice, there's something pretty interesting in the data already. These values are all negative, and some of these are positive. So could it be that it's saying these are science already and these are sport related? You see how it figured out a pattern that it can use given the problem. Got it? But it's not the answer, right? This is just a compression. And these algorithms, if you apply PCA, it's a slightly different algorithm, but you just tell it what compression you want. So from a vector space of R11 to a vector space of R2. Now what we have here is that we know that we can plot these already. Okay. Okay. So I can train a model either with the original ones or with these, right? So that's the other thing. So let's go ahead and try that. So yeah, so this is just an intuition of how it works. So now let's go ahead and plot these because we can visualize these for sure. So if you look over here, I'm just grabbing W0 is just the first column, and then the other one's the other column, and they're XS on the X-axis, on the Y-axis. So I can plot this data. I'm going to run it. Okay, so now we do this. And you can see we have our points. Now I ask you guys the following question. You look at this picture, grab a marker, and draw 2 circles. Where you think, what items belong to circle one and what items belong to circle two. So some people might say, okay, I think these two are in one circle because you can only draw two circles. And then these seem to be in another circle, right? So all of these seem to be together and these seem to be together. And then the distance between these two circles seems to be wider, right? So that is the clustering algorithm. That's what you guys would do. And that's actually what the clustering algorithm will try to do as well, right? It starts with, it picks a random point, and then it's going to measure the distance between that random point and all the points around it, measure those distances, and put points that have the similar distances in one group, and then points that have longer distances in another group. So you can see that there. All right, so visually, humans at this point are able to solve this problem. Obviously, machine learning doesn't work that way, right? So machine learning still needs to work with this data over here, right? And that's where we are going to introduce the k-means clustering algorithm. Okay, so take a look at the data. Machine learning and Python are super fun. Python is super cool. Uh, Data science and Python. Okay, so let's train the model now. K-means. It's gonna try to create those circles. So obviously we bring in k-means first. All right, so we got that. And we instantiate uh, the k-means model. All right, so we want two clusters. It should do this randomly, maximum iterations to 300, and some default values. So let's instantiate it. Okay. And now let's train it on the data. Right. So we are training it on the DTM LSA, where DTM LSA should be DTM LSA should be this data here, right? So the DTM LSA is which the DTM LSA is the original data, I think. Yeah. Oh no, it is. Here it is. DTM LSA is the data after singular value counts. So it's two columns. Got it? So now we're going to train that data on model, and the model should tell us one, two cluster, and it should tell us what cluster each point belongs to. So it's kind of a classification, but based on similar. Go ahead and that was that's actually this one. Okay, so I got it. So I trained the model now. You want the shape, so we should have 7 labels in there. There's 7 sentences. There are 7. And now you print the labels. And as you can see, it works well. You guys see that? So it basically puts the last 2 sentences in one the last 2 sentences in one class, right? Sports, and then the first 5 in another class. Okay. Now, Does it know what those mean? No, it doesn't know that it's science or coding or what. It only knows that it's different. This is one cluster, and this is another cluster. So that's essentially the idea. All right. So now we can plot this information. This is just now we have the labels. Um, we can plot samples just so we can do them. And you can see there essentially that's just like you guys have created. Does this make sense? So you have seen here how to represent text on coding. You have seen here how to compress the data from features 11 to feature 2. And then you have learned how to use clustering to group data into different categories. So there you go. That is the k-means algorithm. Any questions? Pretty easy. All right, so we're going to repeat this exercise, but now I'm going to change the data to something more, more like cybersecurity data. Okay, so let's do that. Okay, here. Okay, so I have a second example. So, you saw it here, right? And you might ask yourself, so how do I use this? Let's go back. So I have this other example, going to be similar. This is an anomaly detection with k-means clustering. But we're going to repeat the same idea. And that's going to change here. There's a data. So we have the library already. We are going to need what's called a guys. So this is token essentially, we're just slicing out every 2 digits from the file. Okay, so let's look at the data first. So let's imagine that this is packet payloads. I guess we network security. Imagine that you have a cybersecurity problem. Right? Now, if you look at these, like you did this for percentages, right? You see two different categories. It's harder, right? It's harder to see here. But this would be accessible data. That's probably going to be in any cybersecurity problem. Right? It's like data and malware, there's going to be text data like payloads or packets. So that's the exact same problem as the text one. Right? So if you look here, right, I'm setting so a network packet, Ethernet, IP header, TCP header, payload, and the payload is carrying the data, maybe a buffer overflow attack, something like that. Obviously not encrypted, right? Because if it was encrypted, then it's rare. So here I kind of, I already know the first 5 are normal, and the last 2 are anomaly. I've made them in such a way. Okay. So what I need to do is I need to and a lot of the time in cybersecurity, you end up thinking in terms of words. So you think of you treat the problem as, okay, this is just syllables or words or something like that. So in this case, that's what I'm doing. So that's why I create this tokenizer, right? This tokenizer essentially just breaks up, creates a list of each one of these. So for instance, I'm going to grab that one. This is just a list. So I'm going to say for, let's say, sent in examples. And then I'm going to hex tokenize. I'm assuming this is hexadecimal. And this is going to sent and R. And I'm just going to print R. Okay. So now let's load the sentences. We already loaded the tokenizer. And as you can see, it essentially creates these, breaks up every 2 digits, right? It's capturing some kind of thing that would be equivalent to the words. And so now what you're going to do is you're going to try to cluster these, right, into things that are anomalous and things that are not anomalous, right? And so that's the idea. You create the two clusters. Does this make sense? So remember, these are normal. These are anomalous, basically. But now you have a machine learning algorithm that can easily be used for anomaly detection. So let's proceed. It's actually the same procedure. So I create my vectorizer here. Copy. It's a little bit different this time around, but that's useful to know. So you can use the count vectorizer and you provide a tokenizer to it. So that's the tokenizer that I showed you how it works. And lowercase set to false. And then that should be it. So I'll run that. That's the vectorizer. So now we fit and transform with the data. Okay, so just a warning. Okay, now we proceed to print the words equivalents, so like hex tokens. So these are the ones that it identified as being the syllables, the vocabulary that makes up these hexadecimal values. And we can print out the DTM array here. You see that there. So I'm using still the same idea of of the bag of words approach from like the previous example. So every one of these up here, right, is now represented as a feature vector of size. I think it's like 14 or whatever the size of this is. Okay, so it's what is it? 3, 6, 9, 12, 15, 17. All right, so now let's look at it as a pandas data frame. And there you go. You can see now each one of these is represented as a feature vector of size 17. And you're just saying, if like, is 00 present in here? Yes. Is 12 present? No. And so on, right? And so that's a representation of it. Once you have that, vectors are numerical, then a huge amount of tools for machine learning become available, such as singular value computation. Right? So we do the LSA truncated FP. So that's created the LSA already. And now we just compress it, fit it times 4. So we don't have to train with 17 features. Imagine now, obviously this was just a few examples, but with real data, how many would you have of these hexadecimal values? There's a lot more, right? So you compress it here, but this is not a very sparse matrix. Um, so we perform that task. That's done. Okay. And then now we can just look at this data frame again, and you will see that right there. Okay. So each one of these has been now compressed to just vectors of 2 features. So once again, this could be plotted, and we want to see if the model I already when I created the data, I created so that the first 5 are normal, the last 2 are anomalous. But the model needs to detect it. So let's see if it's successful. Let's go ahead and test. Then I'm going to plot it before plot it. And the way that I created these matches is similar to my example language. And there you go. You can see that already in the plot. You can start to see that these 2 are kind of similar. These are similar. But let's see. But that's not inclusive enough. You need an algorithm that actually gives a label for each thing, right? Of what cluster they belong to. So we're going to break k-means. And as I said, the k-means is similar to KNN, which we covered at the beginning of the semester. So I start the instantiate k-means. This. Oops. Right? Same thing. I want 2 clusters. I'm going to train the data. And we are going to view, will fit and train actually. So it predicts. And let's see. And there you go. The first 5 are 0, the last 2 are 1. So it's essentially found the same pattern that I introduced. Do you guys see that? So now you could say that the majority is normal, right? So the next time around, when you get a new sample, right, the model is going to tell you if it belongs, if it's 0, then it belongs to this one, so it's normal. And if it's a 1, it belongs to these, and it's an anomaly. Any questions? This is an anomaly detection system, very common thing in cybersecurity, right? So you know what the normal traffic looks like, so you're looking for deviations from it. So that should conclude that example. And then we can just proceed to plot it just like we did before. Same idea. Okay. There you go. Perfect. Any questions? All right, so we covered a lot of topics here. Clustering, we covered singular value decomposition, we covered representation of text data and cybersecurity data via one bag of words approach. No questions on this one? This will be on the exam, right? So Nothing? Everything clear? All right. So in the time we have left, I will cover the last topic for today, which is very interesting. I think you guys will like it. Um, so that's a huge topic that could be a whole course. Okay, it could be a whole course. It's an area of machine learning that you should probably know about. So let's go ahead and do that. Let me copy this in the contents. All right, so the topic is called reinforcement learning. This is another topic where you don't have labels per se, as we traditionally looked at. So we had clustering, we have the normal classification where we have labels, right? Then we have clustering, also called unsupervised learning, where we don't have, man, this thing keeps getting in my. We have unsupervised where we don't have labels, and then we have reinforcement learning. In reinforcement learning, what we have is we have games. In the most classic example, we have games and we have the rules of the game. Do you see what I'm saying? So whenever you take an action, you have an outcome based on the rules of the game, and that's the feedback that you use to train the model. Do you guys see that? So there's a lot of fields here. So there's two big families of reinforcement learning. Some of them are called Q-value algorithms, and the other ones are called proximal policy algorithms. So in the proximal policy, you have something called PPO, DPO, GRPO. Those are the algorithms used to train large language models like ChatGPT. They are, in fact, what makes them really smart. Okay, so chain of thought reasoning, just being able to answer questions, all of that is trained via those algorithms of proximal policy PPO. As I said, this is a huge topic. I'm only going to show very small, and I have like 40 minutes. So I'm going to show more like the Q learning type of approach, which it's the simplest to look at. This was the first like big breakthrough in intelligence and machine learning with reinforcement learning. Happened in around 2014, 2015, when they created a reinforcement learning algorithm that could play the game of Go. If you've ever heard of that game, it's like chess, but much more complex, much more difficult. Chess was, and back, if you remember Big Blue, in the 1990s, they had this very competition on Jeopardy, I think it was, or one of those. And somebody played with Big Blue and a champ, I think, let's say Kasparov played with Big Blue and Big Blue won. And it was just back then more of a heuristic AI versus a purely neural network machine learning AI like today. You guys see that? So chess, they developed a machine that could beat humans in the 90s, right? But the game of Go was much more difficult. And that game, they developed something called AlphaGo, which actually, if you're interested in that, you can go on Netflix. There's a whole documentary called AlphaGo. And they show you essentially how they use something called Q learning and deep Q learning to train a model to learn the game of Go. Um, yeah, the world champion back then was Liu Sedol, I think, from Korea. And it's a very famous match because there's something called move 7 or 17, and it was a move that no one had ever done in the history of the game. Think about that. Like, if you ever played chess, I mean, there's books, right? The Queen's Gambit, the French Defense, whatever. These are like textbook moves that you should do. So humans for years have created these moves. Studied them. I'm sure they've done the same Go, but in 7 or 17, it's like, wait, no one had ever done that. The machine invented that, you know, with its own thinking, right? And so that was huge. So anyway, so they've done, so that's where that history comes from. And then they did also targeting. So the next big thing was they developed a machine learning model. This is 2013, 2015 to play the Atari games. And it did really well, better than expert players. I think it was 80 games and like 70 of them it just looked better, right? So it did that. So and then, as I said, obviously today, the chat GPT that you use for reasoning, you can ask a question always through reinforcement learning. Very advanced concepts, reinforcement learning feedbacks, and these techniques that practical policies of family about this. Yeah, GPO, DPO, which came out this year, just invented a very called GRPO. And it's just a tweak that made the models even more efficient. So that's the last part of the training that is given to large language models like chat. They only use these techniques. All right, but obviously that's huge. That's requires a lot of study. We're only going to look at very specific data that captures how reinforcement learning works. Okay. So I added here the script. So is this once you click on code, this we will have to run not on a different notebook, on um, terminal. So I'm going to open up Anaconda, and then we'll talk about the code. This time, so Anaconda 3 front. So give it a second. Okay, there it is. Oh, I'm in a different thing. I'm sorry. Should have opened it. Okay, should be better now. Yep. So see desktop. TIR. So I'm gonna go the Q learning should be here. Right. So yeah, so essentially these are, you can do Atari, AlphaGo, train large language models, but this is at the very essential thing, right? So we're going to go to very basic, we're going to start with very basic games. One of the most basic, essentially those table games, like tic-tac-toe. That is, in fact, the simplest that you can think of, right? So you guys know tic-tac-toe, you put an X and a zero, and so we're going to start with something like that. The games are Frozen Lake and Taxi Cab. Okay. So I will describe how this works, but let's try to do Taxi Cab. So the Conda environment list. Okay, and should be okay. Get our Okay, so I'm going to take a look at this in class taxi cab. All right, so here it is, this code. We're going to need a library called Gym. So usually a lot of these, you need some kind of a gaming environment, right? So in this case, there's a library called Gym that comes with a lot of these little board games like Taxi Cab, etc. And then you instantiate a model, it's a Q-learning model, and then you have the model play the game. So I'll talk about the code. Essentially, the model is in the state, and when it's in the state, it takes an action. And then once it takes an action, it provides that to the environment, and the environment gives it some feedback back, which is essentially what state you end up with after taking an action, plus, things like rewards, penalties, did you die, did you win, things like that. All right. So there's an environment and an agent. Okay. And so we'll discuss that, a very straightforward way. And there's a loop, and in that loop, you are learning how it should work, right? And this is the code. So I want to see if I can run it first. Really, we just need Jim, so it should run. So let me see. So this should be then Python in class. Okay, no module Jim. I've run this before, but I didn't remember in which environment I ran it. I thought it was this one, but I guess not. Okay, so it's doing something. I kind of want to show you the game first, so that you see what's actually happening. I picked taxi cab because it's got a nice interface. Okay, finally. All right, so training. So what is happening here is it plays the game, right? And every time it plays the game, it tries different actions. It's learning, right? And you give it like 100,000. uh, That's 15,000. So I think it should be 100,000 of these iterations. Um, like so initially it just randomly tries things. So I want to show you I hope it'll load it. But I guess I can describe it just in case. So it's a grid type of a game. It's a taxi cab that needs to pick up a passenger. There's four different stops, like four buildings. And so there's four places. There's the cab and the person that it needs to pick up. So the cab needs to go find the person, decide to pick them up, take them, find a place where they're going, drop them off. And it needs to learn how to do that efficiently. Yeah, so this is happening in the background of this. Every epic, it's doing that exactly. But there is a graphical interface. That's what I'm trying to show you right now, so that you understand it. So let's see. Let's give it a second. I should have maybe started with the other one. What's that? Yeah, this is CPU. This is tiny enough for CPU. This fine. So it should get to 100,000, and that means it's played the game 100,000 times. And each time it gets 100 tries, if that makes sense, like rolling of the dice or something, taking actions. But you can do Q learning, which is a table, or deep Q learning, which is a neural network, which is the representation of the table. But let's see if this doesn't work, I'll try the other one. I believe this is the one. Hmm? Is it like, yeah, I mean, yeah, it should get to 100,000. My computer is terrible. 9,000. Ah, error. Um, iGame is not installed. Run install gym toy text. Okay. All right, so let me see if I can run another one because that one does the training, but so it's Frozen Lake, maybe taxi. Let's try taxi. There we go. All right. So this is the game, right? So um this is kind of how it works. Jim provides this is actually a sophisticated game for Jim because Jim will be just like little text things. But you need a game. The game provides the labels in the form of the rules of the game. You know, if you're in a state and you take an action, you end up in another state, right? And once you're in that state, it gives you back a reward, a penalty. It tells you if you win, you lost, and so on, right? So that's the job of the game. The agent is who decides the action that the taxi cab should take. The taxi cab has, as you can see in this game, how many actions? Up, down, left, right, and also pick up and drop off. What that means is it could get, and this is the person, right? So it could get to the person, but if it doesn't pick them up, it just goes. So it actually has to say pick them up. So you can see it's basically one, two, three destination, four locations, but only one is a destination where the building is. And so in every game, this is randomly placed and the person is randomly placed and also the taxi cab are randomly placed. So you can see also there's barriers. So like it can't go, it can only go up here, right? And so on. And so as you can see, this is totally random right now. So the model is just taking actions. I'm going to go left, right, up, down, pick up, drop off. What it needs to do is it needs to, it picked up the person, or maybe not. No, I thought it did. It's supposed to pick them up. Maybe it pick them up and drop them off. That can happen. And so, and then take them to that house. When it gets to that house, it wins the game. So it gets a higher reward because that's the objective. You need to provide these rewards. Does that make sense, guys? How that works? All right. So it seems pretty difficult, right? It's randomly doing this and it should learn. So now let's go to the other script where we train it and then let's see how it performs. So I think now it should work. So I'm going to have to kill this one here. All right. CLS. So dir. Now we're going to do the in-class one. Like, okay. So that so it's got to train. So it's got to do that thing that it was doing randomly 100,000 times. You have to give it enough room to train, but it's essentially while it's doing that, it's learning. Okay. And then what this little game does, what this little script does is once it's trained, it should play that same animation, but knowing what to do instead of taking random actions. And then we're going to take a look at the code. All right, so it's already at 20,000. Okay, so the code, I provided the link, I believe. Here, right? So it would be this one in class taxi cam. So as you can see, we instantiate Jim, that's the game. Jim make taxi version 3. And we create an environment. You see that? We reset the environment so that we can start playing the game. Then we print out the action space. That's the number of actions that are available. So I think it's 6 actions. And the observation space is pretty complex, right? It's the position where you are, what you're doing, where you need to go. So there's a type of encoding that you have to learn per the specific game. So this is the state representation. Then you start at some state and then you assign it to the environment. And then you can print out if you'd like. You can print out the state and so on. You keep track of things like epochs, penalties, and rewards. And that's the main idea. All right. Then comes this idea of the Q table. So we want to add a Q table, and I'll have to explain what that means. Let me see where it's at. So 77, so almost done. Okay, but yeah, so in this example, the type of reinforcement learning that we will use is called the Q table, which is essentially just a table. Okay, it's going to be a table of states to actions. And so what that means is you look at what state you're in, and based on that state, you figure out what's the best action that you should take. Do you see how that would work? So if you're at this building or at this location with a passenger, go left, for instance, right? But that has to be learned by the model itself. Okay, so so we'll need to start the algorithm here. So let's take a look. Oh, something is running. Okay, so it's running now. Did we miss it? What's that? I may have missed. Sorry. All right, I'll have to close it again. Yeah, I'm not saving the state, so I have to train it and then see the result. All right, so anyway, so just in a quick overview here, right? So you create this Q table, which is essentially the state to the actions. Then, if you notice, you play, right? Let's say 100,000 games. And every time you play, you start a new game, you reset it. So you reset the state, you reset all the variables. And then here, you can have something like when you're done, when you've gotten to the destination, or do 100 iterations here, you start playing the game. So what's the overall idea? The overall idea is you have an if statement to select the action. In the beginning, you don't know anything, right? You have no data, so you basically have to pick actions randomly. Okay. Over time, though, as you have learned, like if you've spent 70% training, then you can start relying on your Q table. So at that point, you start saying, okay, if my state is this, this is the corresponding action that I should use. Okay. And so that's the idea. So the table is, it essentially for every state and every action, it assigns a probability. So it's saying, okay, if you're in this state, the action with the highest probability is the one that you should execute. You see that? So that's why in this if statement, you initially select actions randomly, but eventually you start picking them, given the state, from the Q table. Okay. So once you've selected an action, okay, what do? You invoke the environment and you tell it to take a step. But the environment is expecting an action, right? So it takes that action and notice that it returns a new state, but it also returns parameters like rewards and so on. Okay. And then you store the data that you had in the Q table before and after. Okay. That's the information that you're going to store. After that, if you notice, you have this equation here, which is called the Bellman equation. And so the Bellman equation essentially is recalculating the values of the Q table. Those probabilities, which are also called rewards. So essentially, it's got this formula where it looks at the current value there plus the future value of the reward. And essentially with that is able to update the Q table. Do you guys see that? So it just incrementally, almost like when you change the weights, it's incrementally changing those values. And then that's, essentially what it is. Once you calculate that, you reassign it to the Q table. And that's the training. So that's essentially what you do. The next now the current state becomes, or the new state becomes the current state, and you repeat again. So you go back here, you take an action, whether it's a random action or an action from the Q table. You give that action to the environment. The environment takes a step. It gives you a new state. You save the old state and the new state information and rewards. And then you use this equation called the Bellman equation to update the values of the Q table. And that's what you do over time. And if, oh man, oh, sorry. It's too fast. Yeah, I don't know. But it should work. No, every game the building moves. So yeah, I don't know. I need to wait there. I don't know why. No. This is annoying. I'm sorry. But yeah, anyway, that's the idea. I'll try this one more time and I'll just stand there. Because it learns it really well. But yeah, that's essentially how it works. Reinforcement learning is a huge area. I mean, we've covered it in 40 minutes, right? So you can definitely spend it's a course, a whole semester course. But the idea, as I said, is essentially to, in its simplest form, it's a table of states to actions. The model, given a state, picks an action, provides that action to the game. The game provides feedback, the new state, and then you use that information to re-update the table, the Q table. Okay. Now, obviously, that table can be replaced with a neural network. That's the beauty of it, right? So how do you do that? You build a neural network where you give it the state, and what does it output? The actions. Okay, so I'm gonna stay with this one last time to see if we actually see the game. And then I would discuss that transition from a pure Q table to an actual neural network. But you'll see it's kind of the same thing. But yeah, that's Q table and reinforcement learning. There may be something in my code where I need to tell it to do more iterations of playing the game. I don't understand why. See, it does 100 episodes of just playing, but now it doesn't choose values from randomly, and it's not training anymore. So, sure why this part is not. While we're waiting for this, don't forget, please, that Wednesday is stage 2, right? Stage 2 competition. Also, if time permits, everyone should try to present, right? Next week is term project presentations, your Onyx models. If you want to show me that on Wednesday, that you can do that. That's it? Yeah, good. Yeah, term project. So stage 2 far is this Wednesday, and then term project presentations are a week from today, on Monday or Wednesday of next week. Either of those, but try to present on Monday, right? Because it's meant for some to do on Monday, some to do on Wednesday. Yes. During finals week. Yeah, sorry, I'm behind, but I'll work on it this week. All right, so cross your fingers. It should do 100 iterations.
Deduct it if you don't present.
You should present for sure if you can. Okay. Okay, so it's been doing, see, there it goes. We got it this time. So it picks up the person. It's not crashing or anything. Do you see that? Just it knows where to go. Why? Because it probably picked up the pattern of the game. Do you see why it's so good? It's because it's like the pattern of the game itself is not hard. It kind of knows where it starts, where it go, and so it even picked that up. And so that's why, see, it just goes. That's it. Almost magically, right? But it's because of that. I guess, yeah, it does 100 of these, and you can see every time it's pretty good. Any questions, guys, on reinforcement learning? Does it sort of make sense? I know it's, just briefly, but
These are like positions, the part of the movement, right?
yeah, the building moves randomly. See, it moved from yellow to blue. Now it's red, but the person also moves, and the goal is for the taxi to pick up the passenger and take them to the building. But it's really good because it's figured out, okay, when the passenger is here, the building is likely, so. But yeah. And that's just a very simple reinforcement learning table. The other one, you can do this with neural nets. And like I said, build a neural net where the input is the state, the output is the action. That's it. All right, guys. So yeah, that's it. That's the last lecture. And so looking forward